Today we begin the sorting block. This is one of the last main areas of the course. And as mentioned on the course calendar, we will look at a number of sorting algorithms. And after this block, we will do a few graph algorithms, and that will constitute the end of algorithms and data structures. So sorting. Why do we sort? We sort for efficiency. We sort because if we're dealing with a large pile of data, it is much better to have it organized in some way. And so sorting does not always mean ascending order or something or descending order. It means some way of arranging the data. So that third bullet pretty much captures that fact that the choice of what we consider something being sorted depends on the application. Now, for the sake of keeping things pretty straightforward, we will look at sorting primarily in ascending order, but just realize that as long as we can establish some order, we're able to sort as long as that order is consistent. So we will take the natural ordering then, as mentioned, and if we're dealing with numbers, that's primarily going to be the values of the numbers. If we're dealing with text, that's going to be the usually the alphabetic ordering of that text. So once we choose a criteria then by which we're sorting, we then need to determine how to apply our sorting method to the data that we have for our application. Okay, so efficiency is key. We looked at analysis of algorithms, and measuring efficiency is an important concept. And so it will be so also dealing with sorting algorithms. And so we will try to establish a machine independent measure between the different sorting algorithms, and we will link that to the actual size, usually referred to by the letter N, the size of the data. And so we'll take a look at things like the number of comparisons or the number of data moves. Those are common measures for assessing the efficiency of sorting algorithms. And obviously, as we mentioned, the size of the data plays a key role. Now, since it's pretty difficult to determine exactly in some of these cases, for instance, recursive cases are difficult to analyze, and certainly at the undergrad level, we don't dive very deeply into how to analyze those. We will look at some notional values for big O, and we will link to those when we can. So we will look at the algorithms in terms of again, we're best case, worst case, or average case. The best case is usually fairly straightforward to determine, but it is also not of great use. And the average case can be a little bit difficult. It is probably the most difficult of the three values here to calculate. And finally, the worst case can tell us a lot, and we may want to take the worst case into consideration when we're sorting a large amount of data. So when N is very large. So we may also find that there is a lack of correlation between the number of data comparisons that we make, for instance, and the number of data moves that we actually undertake for the algorithm. And so a lot of the times we will focus on the number of comparisons because we have to do that work anyway. We may or may not move data as a result of a comparison, but we have to make the comparisons. And so a lot of the times we'll just we will focus on the number of comparisons. So an algorithm then is unlikely to be efficient for both. It may be, but it doesn't necessarily have to be. Where it gives you great numbers for both the number of comparisons and the number of data moves. And so we will take a look at our problem. We'll look at everything practically. And the bottom line is that that's what we're trying to do here. We're trying to make algorithms useful to the task at hand. So we're trying to make them practical when they're employed. Now we will focus on determining the complexity of these algorithms, and again we will be counting the number of statements or the number of times that we touch a particular data item or compare that particular data item. Just realize that most of the impact that will be seen as far as an algorithm being quote unquote slow or quote unquote fast will be on large data sets. And so on small data sets, oftentimes the more efficient algorithms don't do as well on small data sets. We don't see much value, and that's because the less efficient ones tend to be simpler to code, and as a result there are fewer checks and it runs more quickly. But as we grow the size of our data set, it's going to be increasingly more important to pick algorithms that are efficient. And for instance, if we're sorting 100 items, we could do it with just about any of the methods we're talking about. If we're sorting 100 million items that are very large in size, we do not want an inefficient sorting algorithm. So we will focus on 9 different algorithms. We will look at 9 of them. We will describe all of them. So what we consider the basic sorting algorithms, these are going to be insertion sort, bubble sort, and selection sort. For those that may not know, these are the n squared big O algorithms. The efficient sorting algorithms that we'll look at are shell sort, which is sort of in a class by itself, and then merge sort, heap sort, and quick sort, all of which can attain n log n in efficiency. And finally, we'll ask ourselves whether certain cases lend themselves to being sorted in linear time, so in order n time, and we'll look at counting sort and radix sort as an example of those. With respect to the sorting algorithms, as we discuss each of these, we should focus on a few topics. Number one is the time efficiency. So what is the big O of the algorithm with respect to the number of data comparisons and or the number of data moves? We'll also look at space efficiency, and that is to say, is additional storage space required, or can I sort the data in place without losing the order? We will also take a look at stability. Stability is an important factor if we sort data items by more than one column, if you will. For instance, if we have people's names broken out into first names and last names, and we want to sort that data, we need to do so by picking a stable sorting algorithm. So stability, what that means is that the order that is in the original unsorted data is retained whenever we have the same key in the sorted data. An example of that would be if, for instance, we have two people named Smith, but that's their last name, that they have different first names. A stable sort algorithm would key in on the value Smith, but it would preserve the original order. For instance, if John Smith showed up before Peter Smith in the original order, that order would be preserved in the final sorted data. So as we talk about these algorithms, ask yourselves these questions. What is the efficiency? What is the time efficiency? Do I need additional space? And is this algorithm stable?